All right, great. And we are recording. Okay, awesome. So this is kind of fruit fly learn word embeddings. This is a super interesting paper, I think. Uh, it's basically about using a formalized version of a certain circuit in the fruit fly's brain to learn how to generate like word embeddings. Word embeddings, I mean, is anyone familiar with that term? Maybe you've worked with natural
Not
language
me.
processing. Yeah, Shayan.
Oh, I said not me.
No. Okay. Yeah. Anyone? Is anyone familiar? Okay. So yeah, let me give a bit of context then. So basically, a word embedding is a representation of a word in a vector space. Basically, what that means is that you can represent a word. So like, let's say you want to feed your word into a neural net, right? Let's say you have a sentence. Um, let's say literally this sentence, right? You have a sentence that goes like this: Can a fruit fly learn word embeddings? How do you feed this into a neural net? Um, One of the first things that might come to mind is you can maybe convert each of these characters into some kind of number, right? Like you could like convert to their ASCII or binary representation, and then you could feed in those characters one by one. Um, So that would potentially work. That's something called character embedding, and it's an even lower level of representation. Um, but the thing is that it turns out if you represent each character as just like a number, right? Like it's binary representation, you don't get a lot of um, you don't get a lot of meaning. The way we usually learn character embeddings is we read a huge corpus of text. Or let me put character embeddings to the side for a second. So I'll just say right now that's not necessarily the best approach. What we do instead is generate word embeddings. So basically, we learn these representations, these numerical representations for each of these words, and there's a number of ways in which we can do that. Um, so the question is basically like, how can I take the word fruit and map it into some huge high dimensional vector space, right? Like usually we'll have 300 dimensions for some algorithms, and some algorithms will generate 768 dimensional vectors. But the specific number isn't all that important. Those are just the semi-arbitrary numbers that some algorithms have chosen. But the question is basically, how do we convert a word into a vector that represents its like semantic meaning? Um, Ideally, we would want the semantics, like this vector space, to have properties like certain words with similar meanings clustering closer together, right? So like fruit and vegetable and banana might cluster closely to each other in this vector space. Um, One other kind of thing that we eventually realized, or not eventually, but it turns out to be quite happening quite often, is that when you learn these word vectors, you can do this like analogization process. So the famous example is that if you generate a vector for king and a vector for queen, or sorry, a vector for king, a vector for man, and a vector for woman, right? You get the vectors for each of these words, um, and then you uh, subtract the vector for man from king, and then you add the vector for woman. Then the vector that you end up with, right, when you perform that like that operation, king minus man plus woman, the vector you end up with is the vector for queen, or it's very close to the vector for queen. So we want our vector space to preserve these kind of semantic properties. Um, and that's what like word embedding is about. There's a number of different algorithms that we can use to learn word embeddings. The most common ones, like earlier, the first one that sort of made it popular was word to vec, like word the number two vec. um, it takes two different approaches here. Actually, let's just do word to vec over here, right? So this is the high level kind of description, right? Like you put in a token, right, a word, and then it goes through this neural net, and you get out this vector representation. And this is just like a image of the kind of semantic space that we get, right? So here they've done a dimensionality reduction just to get it into 2 dimensions, but actually it'll be like something like 300 dimensions that these vectors all sit in. So like long to longer is the same as like fast to faster, right? Like the differences between those two vectors are the same. But what I'm looking for is, or not this one here. This is a good one. So there's 2 actual ways that we can learn word vectors with word2vec. There's continuous bag of words where we're given the context and then we're asked to predict the word. And then there's skipgram where we're given a word and we're asked to predict the context. Basically, these build on the fundamental idea of Firthian semantics or distributional semantics, where the idea is that words that show up in similar contexts are going to have similar word embeddings or representations. So if you have like some sequence of like some sentence over here, right? Like the dog somethinged the cat, right? Then you would probably like predict the word chased, right? Chased is probably like the most likely word to be in between in that context. But also potentially it could be like followed or I don't know, like scared, right? So or ran after if that were a single word. But like the idea is that words that show up in similar contexts are going to have similar embeddings. And basically we just feed a huge corpus of text right into our neural net. And for every single word or almost every single word, we provide it the context and then the individual, we provide the context and then ask it to predict the word. And then after we've done that for a bunch of words, we basically end up with this neural network in between, right? This hidden layer that tells us, that sort of encodes the representation of each of these words. And then we can feed in like the word that we want to embed. And then the output of the layer is going to be the embedding for that word. Does that make sense?
Yes.
Yeah, that was a good explanation.
Okay, thanks. That's good to hear. It is sort of complicated, right? I've given you sort of a really high level overview of the fundamental ideas in NLP in like five or 10 minutes, right? So it's hard to cover everything, but I think this is really fundamental to this paper that we're going to go over. I actually believe this paper doesn't use word2vec. It talks more about glove. Glove doesn't exactly do it in this way, but it's the same idea of words that show up in similar contexts are going to have similar embeddings. And consequently, we decide to use the context that words show up in to learn the actual vector embeddings for each word. So let's actually start looking at this paper. Usually I go over the authors. Honestly, though, I don't know any of these authors. A lot of them seem to be out of IBM research, right? We usually don't see too many papers out of IBM research. So this is kind of cool to see that they're doing some really interesting stuff now. So the mushroom body of a fruit fly brain is one of the best studied systems, right? So this is just a specific kind of part of the fruit fly brain. It has these Kenyon cells, which receive input from multiple sensory modalities. So they're inhibited by this type of neuron, right? We're not really sure what that means. But the key idea here is that it creates a sparse high dimensional representation of the inputs. So it takes in a bunch of different sensory modalities and it creates a sparse high dimensional representation of the inputs. What does that actually mean? It just means that we have a very huge vector, right? Probably like hundreds of dimensions, maybe thousands, we'll see. And it's sparse, which means that only some of the dimensions or some of the elements in that big vector or that big list of numbers are going to be activated. So it's going to be mostly zeros and maybe a few ones. Here they study mathematical formalization, right? So they don't literally use the neurons from the fly's brain. They instead model the neural circuit with a deep learning architecture, and then they use it to learn the correlational structure, right, between words in their context. in a corpus, right? Which is what we just covered, right? The relationship between words and their context is basically what constitutes the word's meaning, at least based on this model of semantics. Um, yeah, and that's like a very common NLP task, right? It's basically just like learning semantic representations. Um, they can generate both static and context dependent word embeddings, right? Unlike conventional methods that use dense representations, they encode semantic meanings in these sparse binary hash codes. Uh, so this is kind of the interesting thing, right? Because over here, they're taking advantage of the fact that, where is it? That the fact that the fruit fly's brain is very good at dealing with these sparse high dimensional representations, and they are taking advantage of that architecture to learn these sparse representations of the words. Um, and they find that even though they're doing this like sparse high dimensional thing, they're still able to get those same kind of semantic space results, right? They're still able to do word similarity, right? Like the words cluster with each other effectively, word sense disambiguation, and document classification, which are all sort of standard like semantic classification tasks. Um, it is shown that not only the fruitfly network motif achieve performance comparable to existing methods, but it uses only a fraction of computational resources, right? Because the architecture has basically been optimized by thousands of years of evolution to perform these high dimensional operations. And also like sparse representations. Obviously, if you use an actual huge vector that's literally just a list of numbers with just mostly zeros and a few ones, it's not going to be any more efficient. But if you use a sparse representation, right, in CSE 30, I believe they do talk about this for a little, how you can actually create a sparse vector representation that is much more information efficient uh, than like a standard vector, because basically instead of storing all the zeros and all the ones, you basically just store the keys for each of those ones. But I'm not sure that's not necessarily what they're doing, but they do say that they're able to do this more efficiently. Okay, so over here they're just talking about deep learning, right? Taking biological inspiration for deep learning is like deep learning grew out of this biological inspiration, so they're just continuing to draw on this biological inspiration, which they think could be powerful. Here they're talking a bit about uh, the structure, right? These are the neurons. So for those of you more interested in neuroscience, not the deep learning side, oh, whoops. This section might be a bit interesting, but honestly, I don't understand exactly what they're trying to convey here. Um, Major modality is olfaction, right? Which just means like smelling, but it's also for measuring sense for temperature and humidity, right? So again, these are not designed for dealing with semantic or linguistic inputs, but they're able to turn them um, into like a linguistic machine, sort of. Um, so they have approximately 2,000 Kenyon cells, right, which are some type of neuron, uh, through a set of synaptic weights. So mm, so the Kenyon cells are reciprocally connected through an anterior paired lateral neuron, which sends a strong inhibitory signal back to KC. So um, it's a recurrent network in the sense that uh, you get this feedback back, right? So uh, yeah, okay. So basically, what they're saying is that you have all these sensory inputs, right? And then these are called the projection neurons, right? That take these sensory inputs and they feed them into these Kenyon cells. The Kenyon cells all kind of combine and output to this anterior paired lateral neuron. And then the output from here actually comes back into these Kenyon cells. Um, they also send their outputs to the mushroom body output neurons, but that part isn't included in their model. Um, so I think the basic idea here is just that like it's a feed forward network, right? Except over here we have this kind of recurrent model, but we'll see later on how they actually use that recurrent structure. Um, right, so it's important to be able to distinguish, right? So The network motif is believed to cluster sensory stimuli so that these stimuli that have similar patterns resulted in similar responses. So this is like on a high level seeming very similar to the semantic task, right? So you want to cluster similar words so that, like, for example, chased and followed, because those are going to show up in similar contexts, and therefore you can like understand the same high level meaning from them. And right, the task has evolved to complete this in a very efficient way. Right here, so they talk about J.R. Firth, Firthian semantics. This is like sort of the famous quote, and the basic idea is that the word's meaning can be accurately modeled by looking at the word's context. So they asked this question, right? This is like the core question. Can the correlations between words and their context be extracted from raw text by the biological networks of KCs, which is like sort of formalized in this figure. Right, so they're basically extrapolating from this sensory model into this linguistic model. And how do those results differ from like the standard word-to-vec versus glove, like word-to-vec, glove, BERT, which are the standard kind of NLP algorithms. Right, and because it's mainly for sensory stimuli, right? But they're able to repurpose it for language. So yeah, over here they're just talking about some kinds of like the potential internal mechanisms of how these neurons work. I'm not sure these are too important. You don't need to be too familiar with these. They're basically just contextualizing this in like the neuroscience community about how the structure actually works. But I think they ultimately, we'll see down here, but yeah, we'll see down here how they ultimately decide to formalize the network. But they just want to emphasize that there's still like an ongoing debate on like how these neurons function. So here they sort of summarize the main contributions. They propose an algorithm that's inspired by the fruit fly network to generate these word embeddings, and they're binary, not continuous, yet they still have the same kind of word clustering and similarity attributes. They result in tighter and better separated clusters of concepts, which is kind of surprising, right? Because usually you'd think if you have a continuous vector, right, where you can tune every single dimension, then you'd be able to better emulate these clusters in this high dimensional vector space. But they show that their binarized version is much more effective at clustering these semantic categories. And they require much less compute time than standard NLP architectures, right? BERT we didn't talk about, but this is like sort of the biggest, like most common word embedding algorithm in NLP right now. It uses something called a self-attention or multi-headed attention, but you don't need to know too much about the internal characteristics. It's basically just the same idea of using the context of a word to generate an embedding of that word. But it internally does it with a lot of interesting neural architectures that make it very accurate and good at doing what it should be doing. Oh yeah, any questions up till this point about like the basic context, the background and everything for this? Okay. Is everyone like following it? Like I just want to make sure I'm not going too fast or anything.
Yeah, it's making sense to me.
Okay, great. All right, so now let's talk about the actual learning algorithm. So how do they model this neural architecture, or how do they formalize the learning of that architecture? So consider a training corpus, right? Just like a huge list of words. If the words come from some predefined vocabulary, then the input to the algorithm is a vector of the size 2 times that vocabulary. So I think this is because they have 2 blocks, right? So there's the context, right, which is going to be the first one that's n vocabulary elements, and then the target. So this is like a one-hot encoding, right? Which basically means we first have this. It's so this we have a one-hot encoding of this size, right, and vocabulary, right? Let's say there's like 100 words in our vocabulary. First, we generate a one-hot encoding of the context, right? Um, and then we generate a one-hot encoding of the target. So they combine those one-hot encodings of the context, right? And then the target is just one word. So first so over here in this example, they have what, 6, like their vocabulary is of size 6, just for the purpose of the example, right? So the first word over here is apple. This is the first context word. Then the target word is stock, and then the second context word is rises. So they generate these one-hot encodings for these, which are arbitrary, right? You basically just pick. You can even like alphabetically order the words and then assign each word in the vocabulary to like a dimension in your list or your vector. So here they say like this third element should be apple. Like this third dimension should be apple, and this this first dimension should be rises. So they combine those one-hot representations into this context. And then for the second block, right, which is also going to be of the same vocabulary size, they just put the one-hot encoding of the target, right? So, which is the word stock that we want to predict. And then you can go along and do this for every set of words in the corpus. And yeah, you basically just get a vector for each of those. Right, so then the window W slides along the text corpus, right? And you generate a training vector. You generate a vector for each of those points in the corpus. So that's the input, right? Then it gets passed into the learning algorithm, and the goal of the algorithm is to learn the correlation between the context and the target block. So now we know the input representation. So here they sort of have a mathematical formulation, right? We honestly don't need to go into this. Basically, the idea is that you want to find the correlations between each of these words. In the numerator of the energy function, the binary encoded W-gram, like word gram, is divided by the probabilities of occurrences of individual words element wise. So again, right, probabilities P are calculated based on frequencies of words in the training corpus. Right. Yeah, I don't think this is too important. I mean, we can come back here if you guys really want to dive into this math. Even I haven't dived into this math yet. But the basic idea is we just want to approximate the probability of any word showing up, given its context words. Biohashing. So after learning is completed, the hash codes for the inputs, right, which is what we want to generate, right? So they're calling their vectors hash codes because they're like sparse and really high dimensional. So they're not going to represent them as vectors. They're going to represent them as these hashes. So given this binary encoded W-gram, right, VA, which is what we generated over here, we are going to output this hashing as 1 if the W mu, which they define over here in the top K of all, if in the top K of all KC's activations, yeah, I'm not sure what this notation means over here. Otherwise they output 0. So yeah, I mean, we can look over here what this means. This W mu is, so W is this matrix of synaptic connections. Okay, so this is actually a kind of core idea, I think. So this W is basically the weights of their actual neural net. So okay, this is my bad. This is actually a really key kind of concept. So this is where they're actually presenting the mathematical formalization of the neural net, which they just showed like the architecture of over here, right? But here they're presenting like how they're actually formalizing it. So W is like the weight matrix of the synaptic connections. And they're projecting from the PN layer, right, which is that those projection neurons that first come into the input, into the KC layer, the Kenyon cells. So since there are 2 times n vocabulary neurons in the PN layer, right, because this is the input, right? So we talked about this input dimensionality up here. So this entire input dimensionality is going to be the size of the PN layer, but then there's going to be K neurons in the KC layer. And this K, they define over here, right? So the objective of the training algorithm is to distribute a set of context target pairs among among K buckets, so that similar pairs end up in similar buckets. So basically, it's a clustering algorithm. So they have K buckets, which we can define, right? This is some tunable kind of number based on how many sort of semantic clusters we want to generate. They basically, the goal of the algorithm is to distribute from this input dimensionality, right, into those K number of buckets. So they do this over here, right, where they basically just take the inner product between this XY. XY is, where did they define this? I think XY is just the, I think it's just the input multiplied by the weights. Wait, so this is, oh, so this is every single, no, wait, no, it is not. Anyone see any other uses of this XY? Maybe they're just redefining the inner product. Okay, the inner product is basically just like the same thing as the dot product, right? I think they're just saying, they're just reformalizing this here so that they can talk about the about like the forward pass, right? So we have this weight matrix, right, that represents all these Kenyon cells over here. And then we take the dot product between this VA, right, which is what is this VA? I believe this is the vector, like the vector input. Yeah, a set of training vectors, right? And a vector of occurrence probabilities. Where where Fj is the probability of observing word J in the training corpus. Okay, so this probability is basically a function of this probability of observing a word J in the training corpus. And I think they just go over each of the vectors in this input in the context. Or no, in the entire, okay. Okay, I think I see this now. So basically over here, they take the probability of each dimension of this input vector, and they divide it by the probability of that word showing up in the entire corpus. So we know that this has to be at least 1, right? Because like every vocabulary word shows up at least once. And then this is probably going to be 0 for most of the words, but for some of the words, it's going to be 1, right? Like the ones that are activated. So we divide those by this, and then we multiply it into this weight matrix. And then this weight matrix is what we actually want to learn over here. So yeah, that's sort of the key idea. Does this make sense? Now you can sort of see how like when you're reading it, like, so I skimmed this paper beforehand, but I didn't think this was like relevant math. Usually when I see math formulas in a first reading of a paper, I just skim past them because usually they're just like proofs or something that aren't too relevant. But here, this is actually very relevant because they're creating this mathematical formalization of the neural net. Usually in a lot of papers, they don't actually do this mathematical formalization of the neural net because they aren't like proposing a new neural net architecture. They might just be applying it to a new thing, or they might just be like tweaking certain parts of the architecture, and they're just like doing proofs for why their architecture is better. But here they're like fundamentally creating a new biologically inspired architecture. So they have to be very rigorous with what they're doing over here. So like this is sort of just like a loss function, right? But this is kind of a key equation over here. Basically, they're saying that they're learning this weight matrix, right, for the Kenyan cells by taking by taking the dot product between each of the elements in the weight matrix and multiplying it with this like probability division, which basically tells you how much to weight each of these words versus like, so for most of the time it will be 0, right? Because most of the time it's going to like, it's a sparse representation. So most of the time this VI is going to like zero out this this entire expression. But sometimes it will be 1, and that's when you actually propagate and you learn something. Or I mean, you learn at every point, but you're going to have like a significant change, right? Because now you see the correlation between this word and like its context. It's okay if you still don't completely understand this. Even I'm sort of like digesting it right now, but this sort of gives you like I think this was sort of good in the sense that you sort of saw how like when you're reading a paper, how you would go about like understanding the math in it. Like each of the, you're not supposed to know what each of these mean, right? Like every paper uses slightly different terminology and slightly different um, what's a word? Terminology is good enough, I guess. Like these symbols, you're not supposed to memorize what W, mu, I means. It's very context dependent, right? They use it up here and they basically define it in relation to everything else. So this is sort of what reading math in a paper is usually like. It's a bunch of jumping around and seeing what each of these symbols means. So yeah, again, they're learning this weight matrix for the Kenyan cells. Let's go back over here to the biohashing. Equation 4 makes it possible to generate the hash codes for both individual words and phrases. I'm not sure what. Oh, because this is like a W-gram, right? This can be like however long you want. So this vector representation doesn't have to be just a single word, which means that we can hash like entire phrases. And that's similar to transformer models, right? We can generate entire vectors of phrases, not just individual words. So here they're providing some intuition over here. Consider the limit when all the words have equal probabilities in the training corpus, right? So P of I is equal to 1 and vocabulary, right? So like every single word has 1 occurrence in the entire vocabulary, and every element of P, right, that probability vector or matrix is going to be that same equivalent value. In this limit, the energy function reduces the familiar spherical K-means clustering algorithm. We can look up at this equation again. Yeah, I'm not sure exactly why that is. I think that is a bit too high level. Probably just simplifies. If you just plug in the P's, if you plug that in for the P over here, there's probably some simplification you can do to get K-means clustering. K-means clustering, again, is a unsupervised learning algorithm that basically just clusters vectors with each other in like high dimensional space. Okay, in this limit, all right, wait. The weights of each KC correspond to the centroids of the clusters of context target vectors. So basically they're saying that each Kenyan cell, sorry, each Kenyan cell corresponds, so like each weight in the Kenyan cell corresponds to an individual cluster. So that's sort of how they get this like really discrete clustering representation we mentioned earlier. the fact that everything is like almost one hot encoded, or like it's a very sparse representation, means that like the weight matrix, right? The weight matrix is structured such that each neuron has its own cluster for those context target vectors. And then the hashing rule assigns active state 1 to the k closest centroids, defined with respect to cosine similarity distance. Honestly, I don't completely understand this hashing function stuff as well. I don't want to spend too much time jumping into it. We will probably understand it once we look into some of the tests we learn, some of the tests they run. So yeah, I mean, let's jump into this. So the Casey network shown in figure 1 was trained on open web text corpus, right? This is just a big corpus of text scraped from the internet, with 6 billion words. Static word embeddings evaluation. So here they're just comparing to the current states of the art, which are like glove and word2vec. I'm not sure how those are state of the art. I think BERT is broadly considered the state of the art, and like the various modifications of BERT. But I mean, maybe they're just talking about like simple, relatively simpler architectures. So here they basically have a data set that contains pairs of words with human annotated similarity scores. This is actually kind of an interesting thing because I'm reading this other paper right now, which talks about how that's like a really bad measure of uh, of like similarity. Like human raters are asked to quantify these relations, and that's like bad because like it requires like conscious effort. So like doing this labeling mechanism is actually like kind of a bad idea. Uh, but I mean, yeah, that's sort of not too relevant here. Um, they have these human annotated similarity scores, right, between these pairs of words. And then they model a similarity score between binary representations by looking at each vector, right? Like the similarity function of each vector is n11 plus n00 over n, where n11 and n00 are the number of bits in v1 and v2 that are both 1/0, and n is the length of v1 and 2. Okay, so they're basically saying to compare the similarity of v1 and v2, you add up, you basically just pattern match between v1 and v2, right? So you basically perform, I mean, how many of you have taken CSE 12? It's basically it's a element wise and between these two vectors, and then you just divide it by the total length. So like the average amount of correspondence between the two vectors. I think that's pretty straightforward, right? And then that's how they quantify the similarity between any two vectors. And then they correlate. The cosine similarity is used for the real valued representations, right? Like the word2vec / glove. And then they showed over here. So over here is the average. Wait, so yeah, these are each different data sets. So here they have a 56.6 correlation between, oh, okay, so these are correlations between their similarity, right? Their similarity that they compute between any two vectors and the human annotated score. So optimally, we would want like whenever we say two words are similar, we would want the human, or like whenever two humans say two words are similar, we would want our algorithm to say the same exact thing. So each of these sort of quantifies the correlation between the human annotation and our annotation, right? Or like our output. So here they show like on a bunch of these different tasks, they perform similarly to glove and word2vec, right? Clearly they're lower on some of them, like here they're like 21, and glove and word2vec are like 20 to 30 points, like 10 to 20 points higher than them. Like for example, on this WS353, they're very similar in terms of performance. And then there's a bunch of different state of the arts, which are probably, I mean, we don't need to look here. It's very like niche kind of things for like specific tasks that people have developed. So basically over here, they're just showing their embeddings that are like completely sparse and almost like binary, right? Uh, they're very comparable to Glove and Word2Vec for these word similarity tasks. Right, it's competitive and binary, yeah. So okay, so they say that it would be more fair to compare it to binarized versions of these continuous embeddings. So they also, oops, okay. So they basically binarize these with some algorithms and then show that it's still like kind of, in a binarized context, the fruit fly embeddings actually outperform all the existing methods. Um, yeah, and then so word clustering, right? So binary embeddings result in tighter and better separated clusters, right? Because of the fact that there isn't really that much space between the clusters, right? In continuous embeddings, you can point to any arbitrary point between these clusters because you can just like slide your floating point numbers however much you want. Whereas with binary embeddings, there's very clearly different different of these like one hot encoded centroids. Like we were talking earlier about how those weights, right? The weight matrix of the Kenyon cells basically represents each element represents its own cluster. So we have these much tighter and better separated clusters than with continuous embeddings. So remember we could like tune K, right? The number of buckets. So they played around with a bunch of different number of clusters and they chose 200. They repeated the same thing for glove, right? So they I think they basically just they might have binarized and then clustered glove, or they might have just clustered glove. Right. So then the average distance between points within a cluster is smaller for their embeddings compared to glove embeddings. At the same time, the distance between the closest clusters is larger or equal for the fruit fly embeddings. So it's between clusters, there's usually more. So I mean, this is exactly like just calling it tighter clusters is like the best way to describe the results over here. So over here, you can sort of see how the average cosine similarity within the cluster versus the max cosine similarity between two closest clusters, right? Fruit fly network isn't really some kind of outlier. It's pretty similar to what is this, green glove 75? So like glove with 75 different clusters, as well as just like the standard glove. I think I'm not sure what the number of clusters for that is. Oh, actually, no, that is not the number of clusters. That is uh, the dimensionality. Uh, oh, so in binarization. So yeah, I mean, it's basically just a dimensionality once you binarize. But the point is that like once you binarize everything and you're on like a level playing field with glove, fruit fly network is not really some kind of outlier. It's very comparable. Um, and here they do context dependent word embeddings, right? So basically in a certain context, um, like words mean different things, right? So the design of Apple's latest iPhone, right, means something different than the filling of sweet apple pie recipe. So like having contextual word embeddings is also very important. They basically show that compared to BERT, they have yeah, I mean, I think, yeah. So over here they compare it, right? Here they have very comparable results for this task. 78.6, right, BERT, which is the state of the art or near the state of the art, and then there's a 78.2, right? Very, very close, especially on this news group data set. For the other ones, it's still very comparable, right? Even here, like 90% correlation. With these contextual word embeddings. Here they do document classification. I mean, let's see if there's anything else important before that. Whoops. appendixes. Okay, yeah. I mean, yeah, we can look at document classification real quick, and we're almost done. Then they compare it with glove word2vec for binary classification, for document classification tasks. Okay. So they have these newsgroup data sets with 18,000 documents in 20 different groups. So like the task is basically to classify into those 20 different groups what a given document is. So here they just showed like some engineering stats of like how they trained it. I'm not sure how. Wait, what? Do they not show results for this? Okay, I think they just do this to show off how like computationally efficient their thing is. Uh, yeah, I'm not really sure. They don't. Oh, what? Okay, wait. So they show it up. I am so confused. Wait. Oh, okay. So these were results for the document classification task. Okay, so this wasn't for contextual word similarity. For some reason, they put this above the document classification header. Just weird law tech things probably. So yeah, I mean, we went over this, right? So they're very good at document classification. Over here is where they talk about the contextual word embedding. Oh yeah, so again, like basically they're showing the correlation between their contextual word embeddings and BERTs, I believe, or no, not BERTs. Their context word embeddings with, I mean, I think it's SCWS. Is this some kind of corpus of contextual word embeddings? Yeah, so these are benchmarks, right? So basically they are, yeah. So basically they're just showing that like even here it's very comparable to the state of the art, which is BERT on these tasks, right? Obviously, um, yeah, I mean they actually have it even higher than word to sense with this W equals 3. I'm not sure what that parameter is supposed to model, but I mean, again, the recurring theme that you see everywhere, right, is that it's very comparable. This model, which they basically just formalized from a fruit fly's brain. Um, yeah, and we went over document classification. So then here they show these engineering stats, the training time, right, for each of these data sets. Simlex seems to, or oh yeah, so as over time as they train, right, their accuracy goes up, right? For Simlex, they don't do very well, but the one they perform best at is this RG65. And we see again like the standard kind of curve in machine learning where it like shoots up very quickly and then it plateaus. Um, cool. Computational complexity. Uh, this is what I mean like when I say like math that isn't too important when you're first reading a paper. This is again like formalization kind of stuff to say, to be able to talk about how effectively this model should be able to perform in terms of like time complexity, in terms of like space it should use. That's what this section is really about. Um, yeah, cool. And then discussion and conclusions, right? Uh, can a core computation algorithm in a fruit fly's brain be repurposed for these word embeddings? And they show that it totally does work. What's it's standard, or like normally in the fruit fly's brain, it's used for like smelling things, right? And handling sensory input like temperature and whatnot. But they're able to repurpose it for various different word embedding tasks, uh, document classification, contextual word embeddings, and so on. Right? They outperform Glove by almost 3% on some tasks, word2vec by 6%, but just barely lose to BERT by 3.5%, right? But like when you take into account the fact that it's so comparable, but then also take into account the fact that it requires so much less computational resources, they say it's like basically the idea is that they're saying that biologically inspired algorithms, we should look to them if we're looking for more compute efficient kind of mechanisms, even if they lose slightly in terms of accuracy. So this is sort of just a case study paper almost in like biologically inspired architectures, and I think it's pretty strong, right? The review for iClear is public here, so like we can even look at some of these about like what people are talking about. Right, so they make some state-of-the-art claims, right? Oh yeah, so this is actually what I pointed out earlier, right? I don't think Love was state-of-the-art for unsupervised embeddings. So someone is basically saying that that they should like remove that claim. The comparison with BERT is mostly irrelevant. I don't really agree with that. I think almost everything should be compared to BERT nowadays because I mean that's what most people are familiar with in NLP now, since like BERT is used for almost everything. Yeah, they have some responses up there. Here's some other review kind of notes, right? It doesn't demonstrate that the method is a useful word embedding for NLP researchers, right? But I just don't think that's the goal of this paper. The goal of this paper is to show that we should look to biologically plausible, like we should look to biological architectures more often because they can be more computationally efficient, and so on. And yeah, they don't go too much into the machine learning perspectives. Honestly, for me, like just because my background is more of like less of like hard machine learning stuff and more of like hand wavy NLP / computational neuroscience stuff, I felt that it was pretty rigorous. But I guess for like the really like ML like core people, like at iClear, right? This is an iClear, which is like a standard ML conference. They would want more rigor than that math that we had up here. Um, right, it's pretty easy to understand, but it doesn't. I still agree with this, right? It could have a large impact on the neuroscience field. So again, like it's a question of why are they publishing in iClear if this seems more to be like a computational neuroscience paper. But yeah, I mean, we can go through more of these. You can check these out if you want as well. But it's kind of cool being able to see the public feedback, right, from other researchers and reviewers. Yeah, that's about it. I think this is a really strong paper. I think now that we've done a couple papers in biologically plausible neural nets, we're probably going to head back into doing brain-computer interfaces for the next couple of weeks, I think. But I'm not sure. What do you guys think? What do you want to do? Or actually, first, are there any questions on any of this paper? I mean, I didn't really pause for questions after like halfway through, I think.
I thought this was a really interesting paper. I didn't know like a ton about NLP before this, so I thought it was cool. Although I agree, maybe more people would prefer seeing BCI stuff in the future. I don't know. I really liked it. This paper, though.
Cool. Yeah. I think there's a lot of people who want neuroscience stuff, and some people who want BCI stuff. So it's like very different kind of types of papers. So I think we're just going to be like constantly jumping between those two broad genres. But yeah. Cool. Any other questions? What do you guys think about BCIs versus this kind of stuff for like next week? Do you want to continue reading more biologically plausible papers or go back to BCIs? All right, great. See you, Cameron. Cool. Are there any other opinions?
I think I'm probably gonna have to reread this on my own.
Okay.
Because I think I got like a pretty good overview of the paper, but there were quite a few specifics that I think I need to.
Yeah, I mean, the math is always like you have to sit through it and like really understand it on your own. Like,
yeah,
until you get an intuition for what each of these symbols mean, it's hard. It's going to be hard to follow that part. But I don't think that's as important as really understanding like even if you understand like the word embedding kind of thing, right? The binarization, and like how the fact that making your representation sparse allows you to have higher computational efficiency while also maintaining relatively comparable accuracy. I think that's sort of the core idea. And like the really core idea is just that we should look to biologically, like the core takeaway is just that we should look to biologically motivated architectures more often because they can be very powerful, just like this one. Yeah.
Right.
Cool. Yeah, I mean, were there any other like key like parts that you were a bit confused about?
I'm kind of new to all of this, so I'm definitely going to look at it again. I agree that the math part was a bit
Yeah, it was
confusing.
mostly the math.
Okay.
Yeah.
Yeah, I don't think you have to worry about that too much. I think
Yeah.
it's
But conceptually, it was really cool.
yeah. The math is always like usually when you do your first paper reading, like your first pass through a paper, just like don't even look at the math. But now that we've like looked at it, you can have a read through yourself and like try to understand what all of these mean. Yeah. Cool.
Sweet. Thank you.
Yeah, thanks. Unless you have anything else, I think that's about it.
Awesome.
Great.
All
Thanks.
right, thanks.
All right. See you guys next week.
Yeah, sounds good. Bye.